Welcome back everyone. Welcome to Math Explorer Infinity. So today our exploration into non-smooth optimization takes a deeper dive with subdifferential calculus rules, right? But before we start, I have a question for you, right? Are you actually willing to enhance your mathematical understanding? If your answer is a firm yes, then I strongly invite you to subscribe to the channel and also share this video with anyone else you suspect might be in the dark, right? However, if your answer is no, well, it may be time for you to reconsider, right? Because we are all about expanding our mathematical horizons, right? So, and also this channel is actually tailor-made for those seeking to improve their mathematical understanding and those seeking mathematical enlightenment. So, having said that, in our last lecture, we actually, we were able to characterize minimizers of functions that may exhibit non-differentiability at a certain point, right? In fact, we saw that a point x bar, right, is a minimizer of the function f, right? Oops. Of a function f, say this function is not necessarily convex. Let me write it down here. So a point x bar is actually a minimizer of a function f, not necessarily convex, if and only if, oops, want something nice. Well, okay, if and only if, this doesn't look bad. If and only if 0 is actually in the convex subdifferential of f, right, at x bar, right? Provided that, our functional f is subdifferentiable at x bar. Okay, but however, this condition here, right, is actually, on its own, is not really useful, right? It gets useful if the function f, right, has more structure and if you have calculus rules on subdifferentials. And also, honestly speaking, one highly obtains subdifferentials from the fundamental definition, right, but rather by applying calculus rules. So in this lecture, we are going to derive the subdifferential of some common functionals, right? Functions that we frequently encounter and that are heavily used in practice. And we will, of course, state some calculus rules like the sum rule, the chain rule for subdifferentials, so those kind of stuff. So, well, we will start with the canonical example, right, which is actually the norm in the norm vector space. So this will be theorem 4.5. Yeah. So for any x in a Banach space X, right? So the convex subdifferential, so let me put it here. Yeah. The convex subdifferential of the norm function, right, at the point x, right, it's actually defined to be, this is actually the set of linear bounded operators, right, such that the duality pairing, x star with x, this is the duality pairing, right, so that this is equal to the norm of x, right, and the operator norm of x star, right, is equal to 1. So this is in the case, this is if x is different from 0, right? And in the case where x is equal to 0, this is exactly the, the closed unit ball in x star, right? This is if x equal to 0. Right? So this will be the definition of let me do something nice. Okay, then let me just drag this a bit now here. Okay, so probably I have to mention that by this I mean the set of linear bounded operator, I mean x star in the Joule space, right? Such that the operator norm of x star, right, is less or equal than 1. Okay, so this is how, the convex subdifferential of the norm function actually looks like. Okay, so let's prove this. So proof. So we will start with the easier case, right? So the first case, you consider the case where x is equal to 0, right? So our goal is actually to show that the convex subdifferential of the norm function at the point 0 is equal to the closed unit ball. Okay, so we don't need to use double inclusion, so we can even go directly. So we have, by definition, probably, no. So we have, say, if xi is actually in the convex subdifferential of the norm function at the point 0, right? This is equivalent to say that, this is by definition, right? To say that xi apply to x tilde, right? At x star, this duality pairing, right? This is actually less or equal than the norm of x tilde x, right? So let me just for your recall, this is typically by definition of convex subdifferential. If you don't recall, if you don't remember how we define the convex subdifferential of a function, so I strongly invite you to watch my my video on convex subdifferential, right? I will put the link. Okay, so by definition you have this, right? So this holds actually for every x tilde, right, in x, right? X different from 0, x tilde different from 0, right? Because for the case x tilde equal to 0, the inequality is trivially satisfied, right? So probably I use another color just to, right, since the inequality, right, is trivial for x tilde equal to 0. Okay, so, and this is again equivalent to saying that, if you look at this, right, remember that this is actually linear bounded functionals, right? So this is actually equivalent to saying that the operator norm of x star is actually less or equal than 1, right? So let me write it down for you. This equivalence follows from, this is by definition of the operator norm, right? Right. So remember that the definition of the operator norm is actually the smallest constant for which say this Joule pairing, right, is less or equal than c times the norm of x in x, right? Duality pairing. So norm of, so this, right, is actually the smallest constant for which this inequality holds, right? But the c in our case here is equal to 1, right? So we know that norm of x tilde should be less or equal than 1, right? Cannot be beyond 1. Okay, so this is basically the proof for the case x equal to 0. So we basically prove that convex subdifferential of this, right, of the norm function at the point 0 is equal to or closed unit ball. Okay, now the second case, right? We now assume that that x is actually different from 0. Right, so and then for this we need to use the double inclusion, right? So we first prove first inclusion, right? That if I have an element in the convex subdifferential, so let xi, right, in the convex subdifferential of the norm of this function at x, right? The norm function at the point x, right? So this means by definition that the duality pairing, right, x tilde minus x, right, x star comma x, this is actually less or equal than the norm of x tilde in x minus the norm of x in x, right? And this should hold for every x tilde in x, right? So let's call this star, right? This relation star, we will refer to it, right? Now, if you successively inserting. So if you insert, if in star you insert x tilde equal to 0, right, and then you also insert x tilde equal to 2x, right, in star, in our relation star. So then this yield that the norm of x in x, right, is actually less or equal than this duality pairing. This would be like 2x minus x, right, but I will just write x. This is less or equal than norm of x in x, right? So you see that there is no room left for, there is basically no room left for this duality pairing, right? Instead of being norm of x. So this means that this duality pairing here is equal to the norm of x in x. Okay, so now just to keep track of what we are doing, right? So it remains, in order to conclude the first inclusion, so it remains to prove that the operator norm of xi is equal 1. Okay, so the idea is the same, right? So similarly, we have for every x tilde in x, right, you have that this duality pairing, right, of xi with applied to x tilde. So this is again equal to, what I'm going to do now is that I'm going to insert a 0, right? So this is again the duality pairing at the point x tilde plus x, right, minus x, right? So I insert it and remove x, right? So nothing has changed basically. So now, by definition of xi being in the convex subdifferential, this is less or equal than norm of x tilde plus x, right, minus norm of x in x, right? So this is, oops. So this is by definition of xi being an element of the convex subdifferential of the norm function, right, at the point x, right? This is basically by definition. Now, if you use triangle inequality, then you see that this is less or equal than the norm of x tilde in x, right? So this is triangle inequality, right? Okay, so this means that this duality pairing of x tilde of xi applied to x tilde. This is also equal than the norm of x tilde in x, and this for every x tilde in x, right? So this means that the operator norm of xi is less or equal than 1, right? Because, I mean, as I said already, the operator norm is actually the smallest constant for which this inequality holds. Okay, so we have this is less or equal than 1, so but we want it to be equal to 1, right? So we are not yet done. So moreover, for x tilde equal to x over norm of x in x, right? Remember, x is different from 0, so this is well defined. So we have that the duality pairing of xi with x tilde, right, in x star comma x, this is equal to, I mean, if you plug in x tilde, right, then you get that this is the norm of x tilde minus 1, right, times the duality pairing of xi with x, right, at the point, I mean, okay, but now we prove that this is exactly, I mean, the norm of x, right? So we have that this is equal to the norm of x minus 1 times the norm of this, right? And this is equal to 1, right? This is equal to 1. So and of course, I mean, so this implies that, put it in color, right? So this implies basically that the operator norm, right, of this is greater or equal than 1, right? So maybe I was a bit fast, right? This is by definition the supremum of the absolute value of this duality pairing. And put x tilde here, so you have a norm of x tilde x equal 1. So this is greater or equal than 1. Okay, so from this we can conclude that the operator norm of this is equal to 1. So this is attained. Okay, now let's go to the reverse inclusion. So for the reverse inclusion, conversely, let x star, right, be a linear bounded operator, right, such that this duality pairing hold. So that this duality pairing is equal to the norm of x in x, right, and that the operator norm of x star, right, is equal to 1. So of course our goal is actually to show that such a linear bounded operator lives in the convex subdifferential of the norm function, right, at the point x, right. So maybe I write it down. So we want to show to prove that x star is in the convex subdifferential the norm function, right, at the point x. Okay, so for that, let x tilde, right, be in x, right. So we have x star evaluated at the point x tilde minus x. I mean, if you apply linearity, right, and yeah, if you apply linearity and then the fact that x star is a linear bounded operator, then you see that this is less or equal than the operator norm of this, right, times the norm of x tilde in x, right, minus this duality pairing. So this is basically by, I mean, linearity, right, of the duality pairing, and also due to the fact that X star is a linear bounded operator. Now, well, by assumption, you have that this is equal to 1, right? So this is known. And you also have that this quantity here is equal to the norm of X. So, oops. So if you plug in everything, then you get that this is even equal to the norm of X tilde in X, right? Minus the norm of X in X, right? So you can probably put this equal if you want, right? Okay, so and hence this inequality is exactly what we need for X star to be the convex subdifferential of the norm function at the point X, right? So this is by definition. Okay, so this is the end of the proof, right? So not really difficult. So in particular for X equal to R, right? So in particular, for X equals R, right? We obtain the subdifferential of the absolute value function, right? So that you know already, right, from the last video. So you saw that the convex differential of the absolute value function, right? So at the point T, see, it's exactly what this will be the singleton one, right? This is if T is positive, right? This will be minus 1 if T is negative, and the closed unit word in R, right? So this is actually the interval minus 1, 1 if T is equal to 0. Okay, so we can also give a more explicit characterization of, of the subdifferential, right, of the indicator functional of a convex set, right? So let C, right, be a non-empty convex set, right? Convex subset of the set X, of the space X. So for any X, right, in C, right, which is again the domain of delta C of the indicator function. So we have that this is probably use another color. Copy this one. So you have that an element X star, right, is actually in the convex subdifferential of the indicator function delta C of X, right, if and only if, this is by definition, X star evaluated at the point X tilde minus X, right? X star comma X, this is less equal than delta C of X tilde, right? And this should hold for every X tilde in X, right? But this is again equivalent to saying that this minus this, right, is less or equal than 0, right, for every X tilde in C, right? Because for every X tilde living outside of C, right, the indicator function is plus infinity, right, and the inequality is trivially satisfied. So okay, we usually refer to the convex subdifferential of delta C at the point X as the normal cone, right? This is the normal cone to C, right, at X. So depending on the set C, we can make it, we can even make the convex differential of this indicator function even more explicit, right? For instance, for C equal to the interval minus 1, 1, for instance, right? We can even prove that. So let me use different color. you can show that, this is not really a big deal, right? You just need to proceed by case distinction. You can actually show that the convex differential of delta C, right, at the point X, that this is equal to, this would be the interval 0 plus infinity, right? This is if T equals to 1, right? So this would be minus infinity 0 if T is equal to minus 1, right? And this would be the singleton 0, right? If T is actually minus 1, 1, right? And the empty set else, right? So if, oops, doesn't look nice. This is better, right? So strongly invite you to show it, right? It's not really difficult at all, right? Okay, and if you are familiar with nonlinear optimization, then you will probably recognize this these conditions here as the complementarity condition, right, for Lagrange multipliers, right, corresponding to the inequality that minus 1 is less or equal than T, which is less or equal than 1, right? So yeah, just sorry, mistake, this is not X but T, right? Okay, because I used T all over in the other places. Okay, so now the result I'm about to state now actually provide a crucial link between finite and infinite dimensional convex optimization, right? So for this, we again assume that so let omega, right, included into Rn, right, be open and bounded. So assume we have an open and bounded domain. So we have theorem 4.6. So let f, right, so let little f, right, so define from R into the completion of R might be proper, convex, and lower semi-continuous. And let function capital F, right, defined from LP of omega, right, into the completion of R, right, with P between 1 and plus infinity excluded, right? So this is defined by f of u, right, is equal to, this will be the integral over omega, right, of f evaluated at the point u of x, right, dx, right. This is, of course, if f composed with u is actually in L1, right, and plus infinity else. So then we have, for every u, right, in the effective domain of capital F, so we have that, together with q being the conjugate of exponent of p, right? So this is q equal to, p minus 1, conjugate exponent. So we have that that the convex subdifferential of our function capital F, right, this is equal to the set of linear bounded operators, right, u star living in the Joule space, right, the Joule space of LP here is actually LQ of omega, such that u star at the point x, right, is actually in the convex subdifferential of little f at the point u of x, right? And this should hold for almost every x in omega. Okay, so let me just highlight some key notions here. So our function little f needs to be convex, proper, and lower semi-continuous, right? And also P should be between 1 and plus infinity, right? Plus infinity excluded. So for this, in this case, then you can actually characterize the convex subdifferential of a functional capital F, right, defined via the integral, right, this way, here. Right, so of course this is so as not to get you confused, this is exactly LP of omega. We drop omega. This is exactly the Joule space, right, of LP, right? Okay. So the proof is, it follows from the definition, right? So I will not prove it, but I strongly invite you to do so, right? And of course, if you have any problem, so feel free to reach out to me, right? You can drop a comment, right? And I will be happy to respond to you. Okay. So also what you have to know is also that in particular, this this actually holds, right? Even if you replace capital LQ with little LQ, right? So instead of defining our function capital F on the space LP, right? If this was actually defined on little l p of omega, right? This also holds, right? What I'm basically saying is that, you can have the same thing with the integral being replaced by the sum, right? By the discrete sum, right? Okay. So instead of having kind of a continuous measure, right? This also holds for counting measure. Okay. As I said at the very beginning, right? One highly obtains subdifferentials from the fundamental definition, right? But harder by applying calculus rules, right? So for convex subdifferentials, right, we have the following rules. So this is encapsulated in lemma 4.7. Okay, so let f, right? So let f, capital F, defined from x into completion of R, right, as usual, be convex, and x in the effective domain of f, right? Then I should also write like this. X in the effective domain of f actually ensures that the convex subdifferential actually exists, right? It's not empty, right? Okay, then we have the following, right? The first property is that, if you multiply, if you want to compute the convex subdifferential of lambda f, right, at the point x, this is nothing else than lambda times the convex subdifferential of f at the point x, right? Of course, provided that lambda is strictly positive, right? And of course, maybe I should write it down. This is actually a set, right? This lambda, this is a set of lambda, say xi, right? Such that xi is actually the convex subdifferential of f at the point x. So just to avoid any confusion or misunderstanding. So the second property is that the convex subdifferential, right, of a shifted functional, right? So say you want to evaluate the convex subdifferential of f, right? Shifted a bit slightly at the point x, right? This is again the convex subdifferential of the function f, right, at the translated point, right, x plus x0. And this is of course for This is of course for x0 actually in x, right, with x0 plus x being in the effective domain of f, right? Okay, so those are the first two properties that we have, right? And the proof is, I mean, it's really trivial, right? I mean, it follows from the definition, so I'm not going to do that. Of course, feel free to go through the proof, but basically follows from the definition. So, however, I mean, the sum rule is a bit more delicate, right? So that is why I have a separate theorem for that. So this is theorem 4.8. And this is actually the sum rule. Okay, so let f and g, so let f comma g, right, be two functionals, right, defined from x into the computation of R, be convex and lower semi-continuous. So, I mean, we need lower semi-continuity, right, as additional property. So I need to highlight this, right? Okay, so and let x, right, be in the intersection of their respective domain, right? Right, then if this holds, then the convex subdifferential of f at the point x, plus the convex subdifferential of g at the point x, right, is actually contained into the convex subdifferential of the sum at the point x, right? And then you have equality if only if, so with equality, by equality I mean set equality, right? I mean, with equality if I want to use a different color. With equality if look for something. Nope, not this one. Okay, if equality if they exist, they write it fully, right? Since there is no space. If they exist an x0, right, in the interior of the domain of f, right? We just put the in the interior of the domain of f, right, intersected with the domain of g, right? So let me just highlight this, right? So right, okay. So the proof again is I mean, it's just I mean, I leave it to you, right? So I mean, it's basically not difficult, right? I mean, this I mean, the proof is it's a bit, I mean, it's quite lengthy, right? But not difficult at all. And of course, you're welcome to, I mean, to drop a comment, right, if you are facing any issue with the proof, right? Okay, but aside this, we also have a chain rule, right, for linear operators, right? And this is actually probably our last theorem. This is theorem 4.9. Chain rule. So let A, right, be a linear bounded operator between x and y. Those are two Banach spaces, right? And say you have a function f defined from y into the completion of R, right? I mean, maybe I need to precise this. This is linear bounded operator. So this is the set of linear bounded operators. So let A be a linear bounded operator, right? And F defined from Y into the computation of R be convex and lower semi-continuous. Let me just highlight convexity and lower semi-continuity, right? And say you have a point X, right, that lives in the domain of F composed with A, right? The effective domain of the composition of F with A. Then you have the following: the adjoint of A, right, apply to the convex subdifferential of F at the point AX, right? This is actually contained into the convex subdifferential of the composition F composed with A at the point X, right? So again, I mean, this A star here actually stands for the adjoint, right? I mean, I actually have a very nice playlist on functional analysis, right? Where I went through adjoint operator, spectral theory. I mean, strongly invite you to check it out, right? So this A star actually stands for the adjoint, and of course, once again, maybe use probably this. Once again, this is another way of, this is a set of A star, comma, say Y star, right, such that Y star is actually the convex subdifferential of F at the point AX, right? So you have this inclusion, right? And of course, you might probably wonder, when do we have equality, right? So with equality, just highlight equality. With equality, if I'm going to use another color again, probably this color here. If there exists, it doesn't look nice, sorry. And it's actually a very nice way to waste time, right? I mean, with equality, if there exists x0 in X, right, such that ax0, right, is actually in the interior of the domain of F, right? The interior. I mean, by this, okay, good. So again, the proof is, I mean, it's really easy, right? So I will not go through it, right? So proof. I mean, this is the first inclusion, right? I mean, the inclusion is a direct consequence of the definition. The definition, right? And also for the equality, you have to work a bit more, right? So we'll try it out, right? For the equality, it's a bit I mean, you have to work a bit more. Okay, so this is actually the end of this lecture, right? Thanks for following along. And I mean, until my next video, keep fueling your curiosity and expanding your understanding of mathematics. Happy learning.